Hello and welcome to today's lecture on minimizing leakage power. We have already discussed various techniques about minimizing dynamic power. As you know, the leakage power is very important and it is increasing as we are going from one technology generation to next technology generation. So, from today onwards in few lectures I shall discuss about how leakage power can be minimized. So, here is the agenda of today's lecture. First I shall discuss about why threshold voltage scaling. As we shall see, threshold voltage plays a very important role in minimizing leakage power. So, we shall discuss about the role of threshold voltage and we shall see how threshold voltage scaling can be done to reduce leakage power. Then we shall discuss about various techniques for fabrication of multiple threshold voltages on a single chip, and that is necessary for realizing low power circuits, particularly for minimizing leakage power. Then we shall discuss about leakage power reduction techniques like transistor stacking, variable threshold voltage CMOS, VT CMOS and multi threshold voltage CMOS, empty CMOS. These techniques we shall discuss in today's lecture. Let us start with why leakage power is an issue. I have already discussed about it. As we are going from one technology generation to the next technology generation, the leakage power component is increasing, and as you can see in 70 nanometer technology, the leakage power dissipation has overtaken the dynamic power. So, not only that, it is becoming leakage power is becoming a large component of total power dissipation, as it is clear from this. So, more than 50%, and also another important issue is runtime leakage power. Earlier the leakage power was minimized only when the circuit was in the standby mode, because in the active condition the percentage of leakage power was insignificant compared to dynamic power. So, at run time people were primarily considering the reduction of dynamic power, but now that is not so. So, even during run time when the circuit is in operation, it is essential to reduce the leakage power. That is why the reduction of run time leakage power has become important. And I have already shown you this particular diagram, where as you can see the leakage power is increasing as we are going from one technology generation to the next technology generation, and requirement is that as it is crossing 50% of the total power, you must stop somehow the increase in leakage power has to be stopped somehow, and what is that somehow we shall discuss starting from today's lecture. As I mentioned, in minimizing leakage power, the key parameter is the threshold voltage VT, and the threshold voltage is actually influences two important parameters. One is your delay. Here the normalized delay has been plotted. As you can see, normalized delay reduces more or less quadratically as you reduce the threshold voltage. That means, smaller the threshold voltage, smaller is the delay. So, from the viewpoint of performance, it is essential to have smaller threshold voltage. So, smaller threshold voltage in a circuit leads to faster operation and higher performance. On the other hand, if you look at this particular diagram, this curve, the red line, that is your subthreshold leakage current, which is one of the leakage current component, and you must notice that on this side that subthreshold leakage current has been plotted in logarithmic scale. Even by plotting in logarithmic scale, you can see it is increasing linearly as you are reducing the threshold voltage. That means, as the threshold voltage is reduced, the subthreshold leakage current increases exponentially. And as you know, as you are reducing the supply voltage VDD, as VDD is reduced to reduce power dissipation, what you have to do? You have to this implies that you have to reduce Vt. Vt has to be lowered. That means, as VDD is lowered, you have to reduce threshold voltage. We have seen that in constant field scaling, but as you do so, it increases the power dissipation. It increases the power dissipation. So, it has become a kind of vicious circle. You know, threshold supply voltage is reduced to reduce the power dissipation, particularly the dynamic power dissipation. As you know, the dynamic power dissipation is proportional to VDD square. Leakage power is also reduced. So, supply voltage reduction, supply voltage scaling is a very important technique in reducing power dissipation. As you do so, you are reducing the threshold voltage, and as you reduce the threshold voltage, power dissipation is increasing. So, it has turned out to be a vicious circle. What is the way out from this vicious circle? You can see, smaller the threshold voltage, smaller the delay, larger is the leakage current. On the other hand, I mean, you can say that low Vt provides high performance. On the other hand, as you increase the threshold voltage, larger is the delay, lower is the leakage current. So, high Vt reduces sub-threshold leakage current, and as you know, in a circuit, the threshold voltage has to be kept in the range of 0.2 VDD to 0.5 VDD to get reasonable performance, at the same time reasonable leakage power dissipation. So, from this our observation is we can scale down the threshold voltage for low voltage low power circuits to increase performance. On the other hand, we can scale up threshold voltage without affecting performance. So, our objective will be to judiciously use both high threshold voltage and low threshold voltage, low VDD and low threshold voltage and high threshold voltage in such a way that we shall not compromise on performance. At the same time, we shall reduce the leakage power dissipation. That is the main challenge of this leakage power minimization, or you can say threshold voltage scaling. So, before we discuss various techniques, we shall discuss about fabrication of multiple threshold voltages, because as you have seen, in a single circuit you will be fabricating transistors of multiple threshold voltages. How can it be done? So, there are various approaches which I shall discuss, and this has been taken from a paper by Kaushik Roy and his group, published in Proceedings of the IEEE in the year 2003. The title of the paper is Leakage Current Mechanisms of Deep Submicron CMOS Circuits. So, in this paper you will find various techniques of realizing multiple threshold voltages, and the techniques are: number one is multiple channel doping, second is multiple oxide thickness, third is multiple channel length, and multiple body bias. These are the four basic approaches used for fabricating multiple threshold voltages. Let us see how can it be done. First one is multiple channel doping. So, multiple channel doping is a technique where within the channel you are will be there is you have to perform kind of ion implantation to achieve some level of doping, and you can see how the threshold voltage is related to the doping concentration Na. So, Na factor is here, and Na factor is also in this factor tau b. So, VTB here is flat band voltage, Na is the doping density in the substrate, and you can see tau b is equal to kT by q into Lx into Na by x, where x is the kind of channel penetration. So, the threshold voltage, how the threshold voltage varies with doping concentration is shown in this particular diagram. Here, as you can see, as the doping concentration is increased from 1 to the power 10 to the power 7 per cubic centimeter, this is the scale in the x axis. So, that means here it is 2.5 into 10 to the power 7 per cubic centimeter, at 2 if you make it more than 5 into 10 to the power 7 per cubic centimeter, if you increase the doping concentration in this way, then you find that the threshold voltage varies from 200 millivolt to 600 millivolt. So, the threshold voltage can be varied by changing the doping concentration in the channel region. However, if you want to realize two transistors having two different threshold voltages, you have to perform ion implantation twice using two separate masks. So, that will indeed increase the cost of fabrication. So, additional masks are required compared to conventional single VT fabrication process. So, you can achieve multiple threshold voltage realize multiple threshold voltage transistors in a single circuit. However, you have to incur additional cost in terms of additional processing steps, fabrication steps and additional masks. So, this is one technique that can be used for realizing transistors with multiple threshold voltages. Second technique is multiple oxide thickness. As you know, you have got a silicon dioxide before on top of the channel. So, here is your source and drain region, this is source and this is drain, and here you put a silicon dioxide layer, and on top of that polysilicon is deposited and this forms the gate. So, this thickness of the silicon dioxide plays a very important role in deciding the threshold voltage. So, it is a common sense that smaller is the thickness, you will require lower voltage to create the channel region, and larger the thickness, you will require larger voltage, gate voltage to create the inversion region in the channel. So, I mean oxide thickness, as you reduce the oxide thickness, you can see you require lesser threshold voltage. So, there are two curves in this are shown in this particular diagram. Here one is with constant aspect ratio. So, this top one is without maintaining constant aspect ratio. So, for short channel devices, as the gate oxide thickness increases, the aspect ratio, which is defined as lateral dimension by vertical dimension, decreases. So, this is a problem particularly in short channel devices. So, if you do not bother about the variation of this aspect ratio, lateral dimension by vertical dimension, then you can get a variation of threshold voltage starting from, you can see little less than 400 millivolt to little more than 600 millivolt, as you vary the oxide thickness from 3.7 nanometer to 7.2 nanometer. So, by varying the oxide thickness in this range, you can achieve a variation in the threshold voltage. So, what does it really mean? Here also, whenever you have to fabricate two different oxide thicknesses, it will require additional marks in the oxidation process. As you know that silicon dioxide is deposited by a process known as dry oxidation. So, whenever you do dry oxidation, then that oxide thickness can be controlled by controlling the time of oxidation, duration of oxidation. So, you have to that means you have to fabricate two different transistors by depositing different amounts of silicon dioxide and by the process by using the dry oxidation process. So, again this will require additional step and the lower curve where the aspect ratio is maintained constant, where aspect ratio is L by the T ox into epsilon Si by epsilon Ox to the power 1 by 3 into W 1 by 3, that is the width, and x into 1 by 3 G. So, if you maintain this aspect ratio constant, then of course, your variation is less, as you can see, as you vary the oxide thickness from 3.7 to 5.7, the threshold voltage varies only from 0.24 to 0.28, you can say close to 0.28. So, there is small variation in threshold voltage whenever you are maintaining the aspect ratio constant. However, if you do not maintain the aspect ratio constant, then you can have larger variation in threshold voltage by having different oxide thicknesses. Okay. So, this is that second technique. coming to the third technique where we use multiple channel length. You may recall that I discussed about a phenomenon known as channel length modulation. No, sorry, channel length roll up, where what happens, as you reduce the channel length, and particularly whenever it is less than, you can say 0.25, little more than 0.25, say 0.3 or so, you can see normally the threshold voltage is independent of the channel length. Threshold voltage does not depend on the channel length. However, you can see around this there is a kind of roll up, VTH roll up. This is known as VTH roll up. The threshold voltage rolls off as you reduce the channel length. So, for small variation of channel length, there is a large variation of threshold voltage. So, this phenomenon can be utilized, and this is known as the threshold voltage decreases as the channel length is reduced, which is known as VTH roll up. So, this happens only in in small dimension transistors, and particularly present day MOS transistors. So, this can be utilized to have multiple threshold voltages by varying the channel length by small amount, and you can see there is a significant change in the threshold voltage. So, a little more than 100 millivolt to about little less than 300 millivolt, there is a variation in channel threshold voltage as the channel length varies from maybe 0.2 micron to say 0.5 micron. So, this is a very interesting technique for changing the threshold voltage by varying the channel length. This is the third technique. Fourth technique is multiple body bias. As you know, normally the substrate is connected to the source and then it is grounded. As you can see, here is a P plus region and that is connected to the source and it is grounded. Similarly, the N well is connected to VDD by with the help of a N plus region formed in this N well. So, this is the normal, this is what is done normally, and in such a case we call that there is no bias, or body bias is 0. What can it be done? This P plus or the substrate can be separated from the source, as you can see, and here also this N well can be separated and you can take out as a separate terminal. Then you can apply different voltages with respect to source. For example, the substrate can be, you can apply different voltage to this substrate with respect to the source, and it has been found that if you apply a reverse voltage here, that increases the depletion region, leading to increase in the threshold voltage. So, application of reverse body bias is to bias to the well to source junction leads to increase in the threshold voltage due to widening of the bulk depletion region, and this is known as body effect. I have already discussed about it. However, whenever you want to apply body bias voltage to the substrate and to the well, you have to use a sophisticated fabrication technique known as triple well technology or SOI, silicon on insulator technology, to provide different substrate bias voltages. So, both triple well as well as silicon on insulator technology are costly fabrication technique, and as a consequence in this you can definitely implement this, but the fabrication cost increases. So, not only that, you will require separate power pins for this substrate as well as for the well, and you will require additional area to for routing those lines, and again you will require some substrate bias control circuitry to apply different bias voltages depending on your requirement. So, this is how, by applying multiple body bias voltages, you can realize transistors of different threshold voltages. Earlier we have already discussed how the threshold voltage varies with the body bias. Okay. Now, coming to the leakage reduction techniques, we can divide the leakage reduction techniques into two broad categories. Number one is known as standby leakage reduction. second one is known as runtime leakage reduction. What do you really mean by them? As I was mentioning earlier, when the leakage component was very small compared to the dynamic power, then leakage power reduction techniques were applied only when the circuit was in standby condition. So, the techniques which are used for reducing the leakage power when the circuit is in standby, that means not in operation, you are not applying clock, you are not applying input. In such a case, you apply some technique to reduce the leakage power. Those are known as standby leakage power reduction techniques. On the other hand, whenever the circuit is in operation, circuit is running, in such a condition you are interested in reducing leakage power along with dynamic power, and those are known as runtime leakage power techniques. So, the standby leakage power reduction techniques, there are several techniques. Number one is known as transistor stacking, second one is variable threshold voltage CMOS, VT CMOS, third one is multiple threshold voltage CMOS, empty CMOS, and actually this empty CMOS technique has become more matured, and this is known as power gating or power management. So, in the next lecture I shall discuss in detail about this. Then there are another technique combining power gating with dynamic voltage and frequency scaling. So, earlier we have discussed dynamic voltage and frequency scaling technique, which can be combined with power gating to reduce standby leakage power reduction, which I shall discuss in the next lecture. And then there are runtime leakage reduction techniques, and there are I shall discuss about 3 runtime leakage reduction techniques: dynamic VDD scaling, dual VT assignment approach, and dynamic VTH scaling, which is also known as VTH hopping in a particular situation when you have got only 2 threshold voltages. So, we shall discuss these techniques one after the other, and today we shall focus on these three approaches: transistor stacking, variable threshold voltage CMOS, and multi threshold voltage CMOS, empty CMOS. So, these 3 techniques we shall discuss today. Coming to transistor stacking, whenever you are realizing circuit in this manner, say this is a 4 input NAND gate. So, where you have got 4 NMOS transistors in series and 4 PMOS transistor in parallel. Now, whenever you do the stacking in this manner, there is a possibility that some of the inputs will be 0 and some of them will be 1. That means, you have got 4 inputs. So, there are 16 possible input combinations starting from all 0 to all 1. So, when all the inputs are 0, all the NMOS transistors are off. When you apply 1 1 1 1, all the NMOS transistors are on. So, in this way you can have 16 different combinations, and those 16 different combinations leads to different number of transistors off in this cascade. So, let us consider the situation when you have applied 0 0 0 0 to this. So, in such a situation all these NMOS transistors are off, however, all the PMOS transistors will be on. So, when all the PMOS transistors are on and all the NMOS transistors are off, you can see although these transistors are small, off, some small amount of leakage current will flow. As you know, there are different types of leakage currents like subthreshold leakage current, which flows even when the input voltage is 0 or less than 0 or less than the threshold voltage. So, this is known as subthreshold leakage current, and because of the flow of subthreshold leakage current, there will be small drop across these transistors. So, the drop will not be much, but there will be small drop across these transistors. So, you can see 14 millivolt is across the first transistor, which is connected to the ground, then 34 millivolt between the drain of the second transistor to ground, then 89 millivolt from the drain of the third transistor to ground, and 2.3 volt from the drain of the fourth transistor to ground. So, that means in such a situation we find this source of this transistor is connected to having a voltage 14 millivolt and this is 0 volt. This is having 39 millivolt and this gate is having 0 volt. That means source is having source is having 34 millivolt and gate is 0 volt. And as you know, for all these transistors we have assumed that the substrate is connected to ground, because the body bias is 0, we have assumed that. So, in such a situation it has been found that when more than one transistor is in the series in the CMOS circuit, the leakage current has strong dependence on the number of turned off transistors. So, the number of turned off transistors will decide how much leakage current will flow, and this is known as stack effect. So, whenever you are having different voltages, we shall see what kind of current variation occurs. Say for example, here we have got a 3 input NAND gate and you have got 8 possible input combinations starting with all 0 to all 1. You can see the leakage current is varying from 0.095 nanoampere to 9.410 nanoampere. So, when all these transistors are on, then you can see the leakage current is maximum, when all the transistors are off, leakage current is minimum. So, when you are applying 0 0 0, the leakage current is dependent on this Q1, Q2, Q4, that means all the 3 transistors are in series. So, the transistor leakage current is essentially decided by the leakage current of these 3 transistors. And when it is 001 means this A is 001, that means this is off, this is off and this is on. In such a case, you can see leakage current is increasing, but leakage current is much less than whenever it is 111. So, we find that highest leakage current is 99 times that of the lowest leakage current. So, the leakage current can be different for different number of transistors are off. Why so? Let us try to understand why this occurs. There are 3 mechanisms involved in it. Number 1 is due to exponential dependence of subthreshold current on gate to source voltage. The leakage current is greatly reduced because of negative gate to source voltage. As I was explaining earlier, as you can see here. So, this is the source is having 14 millivolt and as you know, substrate is connected to 0 volt. That means, substrate is having a reverse voltage with respect to the source, because 14 millivolt is positive with respect to 0 volt to which the substrate is connected. Similarly, for this transistor, the source is connected to is now having a voltage of 34 millivolt, but substrate is 0 volt. So, again a reverse body bias is applied. So, whenever the source voltage is substrate is negative with respect to the source, or of course, in this case we are considering subthreshold leakage current. So, we find gate is 0 volt and source is positive. So, gate is negative with respect to the source in all the 3 cases. So, this is leading to this subthreshold leakage current reduction. So, due to exponential dependence of the subthreshold leakage current on gate to source voltage, leakage current is greatly reduced because of the negative gate to source voltage. Second phenomenon is the leakage current is also reduced due to body effect, because the body of all the 3 transistors is reverse biased with respect to the source. So, as I was explaining, so substrate is connected to 0 and you can all the sources are having positive voltage. So, it is leading to reverse body bias. This is the second phenomenon, and third phenomenon is as the source to drain voltage for all the transistors are reduced, subthreshold current due to DIVL effect is also lesser. So, we have seen the voltages across the transistors are very small, 34 millivolt. As you see, the voltages are 14 millivolt, 34 millivolt, 89 millivolt and so on. So, this is leading to this will lead to smaller leakage current because of that DIBL effect, drain induced barrier lowering. Smaller the drain voltage, smaller will be the leakage current due to DIBL effect. So, because of these three phenomenon, there is a reduction in the leakage current. Now, the question arises, how you will apply the input voltage when the circuit is in standby. So, what is the approach? Now, we know by applying a suitable input combination, you can reduce the leakage current. Obviously, if it is a 4 input NAND gate, in such a case, if you apply 0 0 0 0, that will lead to minimum leakage current. That means, when this circuit is in the standby mode, NAND gate is in the standby mode, you will apply this input combination, so that the leakage current is minimum. However, whenever you have got a complex circuit, you have got a multi-level implementation of a complex circuit. So, you have got different types of gates, and a 0 to 1 input may mean 1 to another input, because of inverters available within the circuit. So, in such a situation, what input combination will lead to minimum leakage current? How do you find out that? So, for a single gate, it is a trivial problem to find out the input vector that produces minimum leakage current when the circuit is in standby mode. But when the circuit is complex, finding out the input vector that produces minimum leakage current is a non-trivial problem. In fact, it has been found that it is a NP complete problem. What do you mean by NP complete problem? That means, you have to apply all possible input combinations to find out which one gives you minimum leakage current. And if the number of inputs is say 50, you have to apply 2 to the power 50 input combinations. So, that may take very large time to find out which input combination will give you minimum leakage current. So, what can be done? Normally, what is done? Input vectors are generated randomly and applied to the circuit, and leakage power dissipation is reduced. So, it finds out the input vector that minimizes the leakage current, that input vector is selected which minimizes the leakage current. So, what you are doing, instead of applying all possible input combinations, you are applying some input combination, a subset of them randomly, and finding out which one gives you minimum leakage current, and that you will use when the circuit is in standby mode. And there is another approach, a probabilistic approach, that eliminates the need to do simulations over all 2 to the power n input combinations, where n is the number of circuit inputs. A small subset of all the possible state is evaluated for leakage. Here, this is essentially a heuristics based approach. So, some heuristics are used to identify a subset which can be used, which can be applied to the circuit, and from that the input combinations which are generated by using that heuristic algorithm, you find out the input combination which gives you minimum leakage power. However, you cannot claim that this is the minimum possible, only you can say that it may be closer to minimum. So, lot of research papers have been published for finding out this kind of input combination, and that is known as input assignment whenever the circuit is in a standby mode. So, this is also known as self biasing. So, you are applying some input combination such that kind of self biasing is taking place, which is reducing the subthreshold leakage current, which is reducing the other leakage currents because of the three different effects that I have discussed. So, this is the technique of transistor stacking that can be used to reduce the leakage current when the circuit is in a standby condition. Okay, now, we shall come to the second approach known as VT CMOS. So, in VT CMOS, what is done? variable threshold voltage CMOS. We have already discussed the technique VT CMOS approach, where as I told, you will be separating out the those pins, that means the substrate pins. So, that means what you will be doing, say you have got a substrate, you have fabricated a NMOS transistor. Say let us assume this is p type substrate, and this one you will make it p plus to apply body bias, and this is n plus, this is n plus. So, this is your source, this is drain, and here is the gate. So, you are not connecting these two, and similarly you will be having a well, and in this n well you will be fabricating another transistor, p type transistor, and the well can be connected to by having n plus region, and this one is your p plus, this is also p plus, source and drain, this is your source and drain of the p type transistor. So, what you will be doing, these connections you will be taking separately, and which are shown here, these two lines. So, this corresponds to the connections taken from the n well, and this connection is taken from the p type substrate. So, what you have to do, you have to apply substrate bias control signal to these inputs. How can you do that? The circuit can be in two modes, active mode and standby mode. So, in the active mode, when the circuit is in operation, what you will do, you will apply different body bias. For example, you will apply VBP, that means that PMOS transistor body bias is 2 volt, and the corresponding threshold voltage is minus 2 volt. Here it has been assumed that the supply voltage is 2 volt, and when the NMOS transistor VBN is 0 volt, that means 0 body bias. So, here that means this substrate bias is 2 volt, means it is effectively connected to VDD. So, effectively 0 body bias, this also 0 body bias. So, whenever both are having 0 body bias, the threshold voltages are minus 2 volt for the NMOS transistor, PMOS transistor, and 0 volt for the 0.2 volt for the NMOS transistor. So, this is the active mode condition, and obviously circuit will be fast, because the threshold voltages are small, and you will get good performance. Now, what you do when the circuit is in the standby mode, that time you apply VPP is equal to 4 volt. So, you apply 4 volt here, you apply 4 volt here, and here you apply minus 2 volt. So, in such a situation, that means this voltage is more positive, 2 volt positive with respect to this particular voltage, supply voltage, and as a consequence threshold voltage of this transistor is now minus 0.6. So, this is the threshold voltage of this transistor, and VPN is minus 2 volt. So, here the threshold voltage of this transistor is 0.6 volt. So, we find that both the threshold voltages are now increased, and for the PMOS transistors it is increased from minus 2 volt to minus 0.2 volt to minus 0.6 volt. For the NMOS transistors it is increased from 0.2 volt to 0.6 volt. So, whenever the threshold voltages are increased, as you know, for every 100 millivolt increase in threshold voltage, the subthreshold leakage current reduces by half. So, here threshold voltage is increased by 0.4 volt, that means 400 millivolts. So, for every 100 millivolt it is half. So, it is 4 times half, 1/4, 1/8. So, it will become 1/16. So, that means leakage current will become 1/16 whenever it is in the standby mode compared to the active mode of operation. So, this is known as VT CMOS approach, where you are applying body bias to the circuit to reduce the leakage current. So, the circuit when it is in normal mode of operation, you will apply 0 body bias, and when the circuit is in the standby condition, you will apply reverse body bias, so that the threshold voltages are higher and leakage current is reduced. So, this is known as the VT-CMOS approach. Okay, coming to the now. Okay, I have already explained all these things. Basic principle is to adjust threshold voltage by changing the substrate bias. Transistors initially have low VT during normal operation, and substrate bias is altered by using substrate bias control circuit, and the threshold is increased by using reverse body bias when the circuit is not in use. I have already explained that. So, this is effective in reducing leakage power dissipation in standby mode. However, whenever you use this technique, additional area and higher circuit complexity is there. So, it will have some additional area requirement and more complexity, because you have to realize those substrate bias control circuitry, you have to take out the pins to those points, layout cost and other area cost will be more. Okay. Let us now switch to another technique, that is your empty CMOS. This empty CMOS technique, here you have got low VT CMOS circuits present here, and we are adding two additional transistors known as slip transistors. So, one PMOS and one NMOS. So, one PMOS and one NMOS transistors are added in series with these two, and this was published in a paper by Mutho et al. Sometime in 1996, and they incorporated the term, they introduced the term multi threshold voltage CMOS, empty CMOS technique. What essentially you are doing, suppose you have got an inverter. This is an inverter. So, this inverter you can realize by using low VT. So, both the transistors you can realize by using low VT transistors. What is being done, in addition to this part of the circuit, you will be adding two more transistors in series. This is connected to ground and this is connected to VDD. Now, you are applying a signal known as slip control signal to both these inputs. So, one is complement of the other. That means, when the circuit is in normal mode of operation, this transistor is on, this transistor is also on. So, in the normal mode, you can say this these two transistors are on, and these transistors are essentially high VT transistors. This is also high VT transistor, this is also high VT transistor. Both are high VT transistors, but these are all on, and so the current that will be passing through it will be dependent on the current of this particular circuit, because both the transistors are on, and if the input is say 0 volt, then the leakage current will be dependent on the leakage current of this transistor. So, in the normal mode of operation, the current that will be flowing will correspond to the low VT transistors, and these points will act as kind of virtual VDD. So, this is your V virtual ground, and this point will act as virtual VDD point. So, this is virtual VDD point, this is virtual ground, and this is in the normal mode. Now, in the active mode, what you do, you make this transistor off, this transistor also. That means, you make this one as 1 and this one as 0. So, when you do that, then this PMOS transistor as NMOS transistor both are now off. So, when both of them are off, what will happen? This point and this point, are no longer virtual ground and virtual VDD. You may say, what current will flow through this? Actually, you may say that now the high VT transistors are in series with low VT transistors. So, you may say that if this is the current of the low VT transistors, and this is the current of the high VT transistors, and this is now connected to ground, this is connected to say VDD. So, current will be dependent on the lower of the two, because they are in series, and obviously when two currents are in series, you know that lower current will flow through this path. As the high VT transistors are having lower leakage current, smaller leakage current will flow when the circuit is in the standby mode. That means, in the standby mode you are making the high VT transistors off, leading to smaller leakage current flowing through this part of the circuit. So, this is the basic idea behind this empty CMOS. So, in empty CMOS circuit you are having both high VT and low VT transistors, and the design flow is more or less similar, except that you will be adding slip transistors which are of high VT in addition to those normal circuit. So, this is the basic idea, and you can say that empty CMOS power gating is a design technique in which a power gating transistor is inserted in the stack between the logic transistors and either power or ground, thus creating a virtual supply rail or virtual ground rail. Here we have seen two transistors, you know this transistor is connected to VDD and this transistor is connected to ground. Actually, later on we shall discuss, particularly in the next class, you will see that any one will actually serve the purpose. You do not really require two slip transistors in series, just one slip transistor may serve the purpose, but when the circuit was proposed by Muthu et al., they proposed two transistors, and whenever implementation is done, sometimes both the transistors are used, but in reality any one will serve the purpose. That means, leakage current can be reduced by having one transistor, either the PMOS transistor which is known as the header transistor, or the PMOS NMOS transistor which is known as the footer transistor. So, either you can have this header or this footer transistor in series as the slip transistor, but whatever may be the case, the leakage current will be reduced because the high VT transistors in series with the low VT transistors, and you get smaller leakage power in the standby mode. So, the logic block contains all low VT transistors for fastest switching speed, while the switch transistors, that means those slip transistors header and footer, are built using high VT transistors to minimize leakage. So, basic idea here is you are not really sacrificing the speed of operation, because when the circuit is in normal mode, the slip transistors are on, and this was verified by simulation, and the simulation result is shown here. So, here you can see three lines shown for the three different supply voltages. The top one corresponds to conventional CMOS with full high threshold voltage. That means, when all the transistors are of high threshold voltage, maybe 0.5 VDD. So, the circuit is realized by using 1 volt supply voltage. So, if the 0.5 volt is the threshold voltage, this will correspond to the delay. As you know, when the circuit is realized by using high VT transistors, the delay will be longer, and as a consequence you get normalized delay higher. On the other hand, you can see when the circuit is realized by using only low VT transistors, this is the curve, the green line corresponds to all the circuits realized by using low VT transistors. So, you get much smaller delay. However, whenever you go for empty CMOS, we insert the high VT transistors in series, then it is definitely increasing the delay by small amount, but it is much less correspond to the high VT transistors. So, we find that there is some increase in delay because of the insertion of those high VT slip transistors, but the increase in delay is not very high, small. So, but leakage current reduction will be significant. In other words, we can tell that leakage current will correspond to high VT transistors, performance will correspond if not correspond to very close to low VT transistors. So, you are getting leakage current corresponding to high VT transistors, performance close to the low FIT transistors. That is what is being displayed with the help of these lines. Similarly, if you consider the normalized energy, we find that in power dissipation or energy, power delay energy is essentially power delay product, that is also very small whenever it is realized conventional low FIT transistors, which is also very close to the conventional low FIT transistors. So, in other words, you are getting significant reduction in power dissipation, leakage power dissipation, at the same time without much compromise in performance. So, this simulation results were published by Mutho et al. As I mentioned in the year 1996. Subsequently, this technique has been matured, and it has been found that empty CMOS can be easily implemented using existing circuits, and empty CMOS reduces only the standby power. Large inserted MOSFETs will increase area and delay, as we have seen, and extra VT memory circuit is needed to maintain the data in the standby mode. These aspects the use of this empty CMOS technique for this is known as power gating or power management technique. This had led to a matured technique known as empty CMOS based power gating, where there will be many aspects you have to consider, particularly you will see how the powering up is done, power down takes place, how to insert the slip transistors. There are many aspects which I shall discuss in detail in my next lecture. So, with this we have come to the end of today's lecture. Thank you.